in chapter 13 part 2, we are going to be learning about the volume of solids. Specifically, we're going to start with prisms. So prisms, they are solids, 3D objects. They have uniform cross-section. So uniform means same. It also means identical. And cross-section refers to the area that is exposed when you make a cut on a solid. Okay, so another name for the cross-sectional area is called the base area. Please don't be confused for the word base. It doesn't necessarily have to be at the bottom. So a solid, for example, in this case, a prism, a cuboid, you can make it stand on any of its surface. So the base area, the cross-sectional area, does not necessarily have to be at the bottom. So let's take a look at the first example. In this cuboid, they have shaded the cross-sectional area. So if we were to slice this cuboid, we will end up with identical, in this case it appears to be squares. Okay, so here we have one slice. Here at the end, we have another slice. You notice that all these, they are identical to what is shaded. Similarly, for the next diagram, in this case, it has a cross-sectional area of a triangle. So if we make it transparent, we see that we can actually cut this solid and we will end up with the same triangle that is shaded. So we say it has uniform cross-section. Likewise, for this, the third, fourth, and fifth ones, we can choose to slice it horizontally, and we end up with the same cross-sectional area. Okay, so in this case, you can draw it this way. The top shaded portion, you will find that it is exactly the same as the bottom shaded portion that I'm shading in red, as well as any other cuts that you can make through the middle of this figure. So the very first skill that you need to have is to be able to identify where the uniform cross-section is, if it does exist. So in this particular case, all these solids above, they have uniform cross-sectional areas. Now, again, for the first example, which is a cuboid, it is a prism because it has a uniform cross-section area. I'm now going to shade this uniform cross-section area. It has horizontal length denoted by L. It has a vertical length denoted by the letter B. The area of this cross-section is simply given by L times B. Next, if we want to find the volume, all we need to do is to imagine we have many pieces of this cross-sectional area, which is like a piece of rectangular paper, like an A4 paper. We're going to stack all these pieces of paper up, and we will end up with a cuboid, as shown on the left. So we're going to add another piece of paper to it. We're going to add another piece, and we're just going to keep adding until we get our cuboid. So the volume depends on the thickness over here. The more pieces of paper that we have, the greater the volume. So in this case, we're going to denote this distance by the letter H. Okay, so we are going to take the cross-sectional area, which is L times B. We're going to multiply it by the letter H, in this case the thickness, and that will be our volume. And this is the formula that you have learned for the volume of a cuboid. It came from the idea of stacking together multiple pieces of the uniform cross-section to get the volume. So this is our general formula. for finding the volume of a prism. Now let's move on to another type of prism. In this case, something very familiar. It is a cylinder. So this, in this case, it is a closed cylinder. It is not open. So it's fully solid. Okay. Now it has two circular end faces. One, and at the bottom, another one. So it appears oval. In this case, because we are trying to draw a 3D object. But if you look from the top, you look from the bottom, you'll see a circle. And it has a uniform circular cross-section. It has a base, a radius. So this radius refers to top radius, bottom radius, they're the same. And a vertical height. So imagine that we are... Okay, first let's shade the cross-section area. So there are a few options. You can shade, either shade the top or you can shade the bottom. Okay, so now I will just shade the bottom first. This is my cross-section area. And you can easily find the area. Okay, so that's given by pi r squared, where r is the radius. Now we're going to stack many pieces of this circular piece of paper. We're going to stack them upwards. Stack, 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 and we will end up with a cylinder. The volume of this cylinder depends on the number of pieces of paper that we stack, number of circular pieces of paper. So we are definitely going to have to include the height into our calculation. So if we just remember this concept, it makes our memorizing of this formula really easy. It becomes intuitive. So take the cross-section area, in this case, area of a circle, times the height. So we get pi r square h, where r equals to radius. Now let's move on to the next part. Complete this table. So in this case, prism, triangular prism. Let's give it a name, triangular. Draw the cross-sectional area. So for this particular prism, we can see that it has 5 faces. Not all of them are uniform cross-sectional areas. Okay, so we see 3 rectangles and 2 triangles. What do you think will be the cross-sectional area? So we can pause here and think about it. When you're ready, continue playing to check our answer. So if you say that the cross-sectional area is a triangle, then you are correct. Because that's what we saw earlier on already in the first part of the notes. Okay, so we're going to draw it. This has a perpendicular height h. This is a base of b. So the cross-sectional area is given by half times the base times the height. Now we come to the volume. So volume is given by the cross-sectional area multiplied by the perpendicular height. So now it becomes a little confusing. Okay, so this height and this height, are they the same height? Because in our formula for the area of a triangle, we call it half times base times perpendicular height. And in our calculation of the volume of the prism, we have the area of cross-section multiplied by the height again. So we have to remember that in this formula, for the calculation for the volume of the prism, this height refers to, it is related to how much of the uniform cross-sectional areas you have stacked up. The more you have this uniform cross-sectional areas stacked up, the greater this height will be. So based on that, we know that for the formula, I will just put it here for convenience. So the volume cross-sectional area times the height. This height refers to this distance. It shows us how many pieces of the uniform cross-sectional area we have stacked together. So therefore, our solution will be half times base times height. So far, I've written down the cross-sectional area. multiplied by the perpendicular height, which is given by L in this case. So you can try the next one by yourself. This was already done previously. This is just a rotation of the cylinder, and I'll just talk a bit about the last one. This is a trapezoidal prism. The cross-sectional area is a trapezium. Put in the different lengths that is given, A, B, H. This is for the cross-section. So the cross-sectional area is given by half times the sum of the parallel sides, A plus B, times H. Okay, it wasn't indicated in your notes, but these are parallel lines, so that's why it is a trapezium. Then we move on to the volume. So our cross-sectional area, which we found, half times A plus B times H, multiplied by the perpendicular height. Again, a little confusing because hey, we've got a perpendicular height for the trapezium, and then we've got the height for prism. In this case, our height for the prism is L. And this is our answer. You can, in fact, you should remove the brackets for H. So half A plus B. Okay, let's rewrite it in a neater way. You can put it as half HL A plus B. Okay. Now you can try the rest of the questions in section A by yourself. Section B is slightly more challenging. A tip for you is to break up the cross-sectional area into different parts. And sometimes you need to do a little bit of a subtracting. So for example, in this case, we can find the cross-sectional area for this particular shape by taking area of the rectangle minus area of this semicircle. So be creative about it. Next, this represents a hole in the center. This is a hole. So our cross-sectional area will be a circle. Take away the area of this square. And you can try the rest by yourself.